So how did I define it? I defined it as I is r square dm, where I have a fixed pivot point, fixed axis, and r is essentially the distance of my small mass dm from that axis. Okay, so let's find the moment of inertia for a rod uniform density through its edge. So what I would like to find out is if I actually have a rod which has a total mass m and length l, and it's uniform, if I rotate it with frequency omega, what will be the kinetic energy? It will be 1/2 I times omega square. So I would like to find out what I is. Now, how do I do that? I is integral r squared dm. So I need to choose some small mass. I need to separate this into small parts. So let's say this to take the axis along the rod to be the x-axis. If I take a small section of thickness dx, which is x away from my pivot point, what will be my dm for this small part? If the full mass of the rod is m over L times dx should give me the mass of that small part. I'm basically just taking a linear proportion, right? What's the distance of that point from the axis? It's going to be x, right? So that's what my x is, which means my moment of inertia in this case is going to be x squared times, instead of dm, I'll write m over L dx. How about my limits? I'll start from 0, go all the way to L. So m over L are constants, integral x squared dx from 0 to L. Extremely simple integral, m over L, x cubed divided by 3, evaluated at 0 and L. So it's going to give me m L cubed divided by L over 3. So 1/3 m L square. Now, let me make one thing very clear. Moment of inertia depends on two things. One is the shape of the object. The second one is the axis of rotation. It depends on both. It's defined, for example, I defined the moment of inertia for a rod rotating around the point at its edge. Let me do the same problem. Find I for the same rod rotating around its center of mass. So I'll have the same rod again. It has a length L, but now my 0 is exactly at the center. Okay. So I'm going to rotate around this point. Now, Let's take this to be the x-axis. What do? Again, I split my rod into small parts, small dm parts. Right? So if I have, so this is going to be dm if this distance is dx. dm again is going to be m over L times dx. The formula for I was r squared dm. And r will be, again, x. So my moment of inertia is going to be integral x squared m over L dx. Nothing has changed. But now, what are the limits of this integration? X goes from minus L over 2 to L over 2. So now let's do the integral. I have x cubed over 3. It's the same integral, but the limits have changed. So m over 3L, L over 2 cube minus L over 2 cube. M over 3L, L cube. This is basically just twice minus sign to the cube is minus, so it makes it a plus. Right? So all in all, it's going to be m L square over 12. And I center of mass. And this thing I'm going to call I edge. So case, and why did I calculate these two quantities? I want to emphasize that the moment of inertia around the edge is not equal to moment of inertia around the center of mass. These are not the same quantities. The object may be the same, but rotation axis changes the center of mass. It turns out you can actually relate moments of inertia around different axes to each other by a theorem. It's called the parallel axis theorem. If, let's say this is my center of mass. If I know the moment of inertia around center of mass, moment of inertia around another axis, which is a distance d away from center of mass, is very simply moment of inertia around center of mass plus total mass times d squared, the distance from that center of mass square. I'll not go ahead and prove this. Actually, I think you know enough calculus if you're inclined to learn more physics. It's a good challenge. Try to prove this parallel axis theorem, right? But it also tells you one thing. The moment of inertia around center of mass is the minimum possible moment of inertia for any object. So it's actually, again, the center of mass is a very, very special point. Moment of inertia around is the smallest possible I for any object. Let's check. I told you that for a rod, I edge was 1/3 ml square, and I center of mass was 1/12 ml square. What's the distance between these 2 points? L over 2. So is I edge equal to I center of mass plus m L over 2 square. Let's check. This is going to be 1 over 12 ml square plus m L square over 4. 1 over 12 plus 1 over 4. 1 over 12 plus 3 over 12 times ml square. This is 1/3 ml square. So it checks. So we did our calculations correctly. Okay. So this essentially means that if I know the moment of inertia through the center of mass of an object, all other moments of inertia parallel to that sense of rotation can be easily calculated. Okay? So in reality, people have calculated moments of inertia for most symmetric objects already. And it's quite possible that you'll be given a list of moment of inertia in the exam or whenever, and if you look at your book, you can find list of moments of inertia through the center of mass. But you need to know how to utilize this parallel axis theorem for rotation along other axes. Let me calculate moments of inertia for two different objects because they are easy. For a ring, so if I have a ring, a circle of mass m and radius r, and that's rotating around its center of mass, what is moment of inertia? Well, this is actually quite simple. Why? Because, so let me draw the top view of this. Top view is just a ring. If I take a small piece dm of that ring, what's the distance from the origin? It's r. Does it change with where I choose that dm? No. So integral r squared dm is essentially integral r squared dm. It doesn't depend on where I choose my mass, right? That's excellent. What is integral dm? It's the total mass of my ring. So for a ring, moment of inertia is m times r squared. Let me calculate the moment of inertia for a uniform disk. So again, if I look at the system from the top, I have a disk of radius r, which is uniformly filled, and it's rotating around its center. How do I do this? Again, moment of inertia is going to be r squared dm. But now that I know the moment of inertia for a ring, maybe I can split up my disk into concentric rings, like an onion. Okay, so what I'll do is, I'll say if I have a radius r, I'll choose a thin slice of thickness dr. So I would like to calculate the moment of inertia of that slice. What would be the moment of inertia of that ring? Whatever, I mean, we've just found it for a ring, it's mr squared, so it must be dm times r squared. So how about dm? How much mass is there inside that ring? Well, if I know the area of that ring, maybe again I can do this direct proportionality. Full mass of my disk is m, full area is pi times r squared. Now I will basically calculate the area of this thin slice and do a direct proportionality. Does it make sense? Are we on the same page? I'm just calculating the area of that thin slice. Now what's the area of this thin slice? So I am basically interested in the difference between two circles. The outer circle has radius r plus dr. Inner circle has radius r. So if I expand this, I'll find pi r squared plus pi 2r dr plus pi dr squared minus pi r squared. Pi r squared is cancelled. Do you remember what I told you about differentials? Differential was a number smaller than any number you can think of, but not zero. Okay. So which of these are more important, 2r dr or dr square? 2r dr is much more important. Actually, you can just take dr square to be equal to 0 for differential. So it's 2 pi r times dr is going to be my area. And here is another interpretation. Think of this thin ring. If I actually cut it from one side and opened it up as a rectangle, one side would be dr. How about the other side? It's basically the circumference of the circle. So it's going to be 2 pi r. And if I multiply 2 pi r by dr, I actually find the same area. So if you go ahead and learn some differential geometry in the future, you'll find out whenever you can actually take curved objects and flatten them, or whenever you cannot do that. In this case, we can do it. For differential objects, the curvature is not going to matter to us. All right? So that's good. Let me just write it there. It's going to be m over pi r squared 2 pi r dr. So di is dm times r squared. I'm just writing what I have here. Let me r squared dm r squared times m over pi r squared 2 pi r dr. So what's the total moment of inertia? R squared m over pi capital R squared 2 pi r dr. What are my integration limits? These thin slices will start at 0 radius and go up to capital R, all the way to capital R. So it's going to be pi is cancelled, 2m over r squared is a constant, 0 to r cubed dr. The integral is r to the 4 divided by 4 at 0 and r. So it's going to be 2m over r squared, r to the 4 divided by 4, or I, center of mass for a disk, is m r squared over 2. All right? So moment of inertia in many cases can either be found by straightforward integration or can be actually looked up in some lookup table. People have listed, your book has a list of moments of inertia. for different objects, we've done the rod, we've done the disk, but for example, if you actually have a rectangle at its center of mass, that's a uniform rectangle of AB, what you would actually find is moment of inertia rectangle is, if I remember correctly, m times a square plus b square. All right? For a sphere, uniformly filled sphere, it's 2 over 5 mr squared. All right? Now, we could go ahead and do integration and find those quantities, but it's really not useful at this point. Let me concentrate on how to use moment of inertia in my dynamical equation. So rest of the lecture, I'll actually think that moment of inertia is given, and I'll try to solve torque equals I alpha equation. Right? Now I've actually replaced force by torque, mass by moment of inertia, and acceleration by angular acceleration alpha. So let's solve an example. Let's solve the example we were actually looking at the start. I had a wheel where there was M1 and M2. Now I'll actually tell you that the wheel has some moment of inertia. Let's call this T1, T2. Find T1, T2, and angular acceleration of the wheel. All right? I gave these radii as A and B. So when I let the system go, if M1 over M2 ratio is not exactly B over A, this wheel is going to rotate left or right depending on M1 and M2, right? One of the masses is going to go down, the other is going to go up. And the wheel will start rotating with some angular acceleration. Let's find out all those quantities. Right? How do I solve such a mechanics, such a dynamics problem? I look at free body diagrams. The answer has not changed. Okay? So let's actually look at free body diagrams. But before that, let me assign some directions. Let me say M2 is going down, and it's going down with some acceleration A2. M1 is going up with some acceleration A1. And this wheel is rotating with some angular acceleration alpha, okay? I'm making these directions up. If at the end of the day I'm wrong, I'll just find negative numbers, right? That's how it worked. So, free body diagrams, as always. For M1, what do I have? I have T1 pulling it up, M1G pulling it down, and its acceleration is A1. So M1 times A1 is T1 minus M1G. How about M2? M2 is being pulled up by T2. It's pulled down by M2G, its weight, and it's accelerating down with A2. So M2 times A2 is M2G minus tension 2. Now, how about the free body diagram for my pulley? Now, am I interested in F equals ma for this pulley? No, because it's not going to move. It's nailed to the wall, right? But that's not the only Newton's equation I have now. I also have torque equals I times alpha, right? So this is going to rotate with some alpha acceleration. Now, here I have m1g, and here I have m2g. You are right. Excellent. That is T1 and T2. That's an important point. I look at free body diagram. I'm just looking at the forces applied on the pulley. Okay. Now, I need to write torque equals I times alpha. I is given, so I need to write the torque. But here, please follow me instead of taking notes. This is important. How do I find the torque here? So T2 is acting with a radius of B, while T1 is acting with a radius of A. The angle between the radii and the force is 90 degrees. Now, I rotated alpha to be clockwise. I choose alpha to be clockwise. Which force is trying to rotate the wheel clockwise? Is it T1 or T2? T2, which means its torque must be positive. So T2 times B is the torque that's trying to rotate my pulley clockwise, minus T1 times A is trying to rotate it counterclockwise. That must equal I times alpha. Could you close the door? Now, so that's my third equation. That's my second equation. That's my first equation. The trouble is that I have far too many unknowns, right? I have A1, A2, alpha, T1, T2. 5 unknowns, only 2 equations. I need something else. These objects are not moving independently of each other. So there must be a connection between their accelerations, right? So, okay, so that was a very bad choice, but A1 and A are different things, right? That's a length, not an acceleration, everyone. Should be clear. A1, A2, and alpha must be related. Let's think about this wheel. Again, please do not take notes, just follow me. Now, if this wheel pulley rotates by an angle theta, what happens to M2? If it rotates clockwise by an angle theta, this thing is going to go down. How much is it going to go down? The radius here is B. All the rope around this part will now become added to the length, right? So the distance it actually falls down, let me call this delta 2, is going to be B times theta. How about m1 though? What will m1 do? M1 actually going to go up. I messed this up. Okay. M1 is going to go up. By which amount? Let me call this delta 1. Delta 1 is going to be, well, both objects are rotating, so it will actually rotate by delta. So this part of the radius will be subtracted from the length, right? So delta 1 is going to be a times theta. If I take two derivatives, two-time derivatives of delta 2, what do I find? It's going to be exactly a2, the acceleration of the second mass, which is going to be apparently b times d square theta dt square. What's that? It's the angular acceleration alpha. So a2 is b times alpha. Similarly, a1 is a times alpha. Now my three equations, I have 5 equations if you want. I can solve them. Let me rewrite these. m1 times a1 was t1 minus m1g. m2 times a2 was m2g minus t2. And I times alpha was t2b minus t1a. What I can do is, if I multiply this equation by b, or a, I'm sorry, m1a times a1, I don't want to do that, I'm sorry. Let me. So I would like to, instead of a1, I want to write everything in terms of alpha. Okay? That's what I actually want to do. But I have t1 and t2. I want to get rid of these t1 and t2. So I'll do the following. I'll write m1a times a1 is t1a minus m1ag. But instead of a1, I will just write a times alpha. Is that okay? Similarly, so here I multiplied by a, and here I multiply by b. I'll write m2b times a2 is m2bg minus t2b. And again, I can use a2 here. It's going to be b times alpha. So my new equations are m1a square alpha is t1a minus m1ag. m2b square alpha is m2bg minus t2b. And the final equation is I alpha is t2b minus t1a. Now I can add all three equations together. I'll find I plus m1a square plus m2b square times alpha is t1a's cancel, t2b's cancel. I have m2b minus m1a times g, or I've found the angular acceleration m2b minus m1a divided by I plus m1a square plus m2b square times G. Excellent. Does it make sense? There is a very simple limit, the limit I've actually discussed previously. If M1A is equal to M2B, what should alpha be? Alpha should be 0. That's the equivalence condition. Did I find that? So that limit actually checks in my answer. How do I find A1? A1, I already know. It's going to be A times alpha. A2 is going to be B times alpha. How about the tensions in the rope? Well, T1 would be M1G plus M1A1, okay? From the first equation. And T2 would be M2G minus M2A2. Right? You can actually plug in, now that I found alpha, I'll not lose time doing this plugging in, but you can find all as quantities. Question?
So could you explain that part when you found this one?
That's fun. Let me try to explain it in the next example, okay? So I'll do the same thing again. So let's maybe solve a simpler system. Just some mass m tied to a disk of radius r and total mass, let me call this m2 and m1. Find the acceleration of the mass m2. Now, how do I solve any dynamics problem? Again, I'm actually just applying Newton's laws individually to each particle. Here I have two particles, so I draw the free body diagrams. For M2, let's call this tension T. So for M2, I have M2G down and T up. Let's say it has an acceleration A going down. So I'll have M2G minus T is going to be, hey, that's going to be my first equation. How about just a single pulley? What will be my equation here? Am I interested in F equals ma? No, this thing is not moving. Its center of mass is fixed. But I'm interested in torque equals I alpha. So let's say it rotates clockwise with alpha. What's the torque? T times R, because the angle between them is 90 degrees. So torque is equal to T times R must equals I times alpha. But what is I? This is a disk. So we've actually calculated the moment of inertia from the center of mass. That was mr square over 2. So if I write this, substitute T times R is mr square over 2 times alpha. R's cancel. So mr over 2 alpha is equal to T. I have two equations. But how many unknowns do I have? I don't know A. I don't know alpha. I don't know tension. So I need one more equation. Obviously, how much that mass goes down depends on how much my pulley rotates, right? So there must be some relation between acceleration of the mass and the rotational acceleration, the angular acceleration of the pulley, right? So how do I find that out? Let's say this is my initial position. If I rotate the pulley by an angle theta, what will happen to the mass? It will actually go down. Why? Because I assume that my rope is not stretching. Okay. So all the parts of the rope here, all the length of the rope, which is going to be r times theta, must be added essentially to the end of the string. Right? So how far did this guy go down? It went down with the length on the surface of the circle, with the arc length, which is r times theta. Does that make sense? Is everyone following me? Should I repeat the argument? If I rotate the disk by theta, the mass goes down by r times theta. Question?
Because the rope is not slipping.
Yes, because the rope is not slipping or extending, right? So if I take a derivative of delta, r is a constant, that must be a time derivative of theta. That's going to be my velocity going down. That's going to be r times omega. That also makes sense, right? If the edge of my pulley is moving with velocity v, that must be exactly the velocity of the mass going down, and that velocity is r times omega, as we have previously defined. But if I take one more derivative, I find that a is r times alpha. Now that would be my third equation. Okay, so I can solve those three equations. Let's write them. M2G minus T is M2A. First equation. Second equation is MR over 2 alpha is T, right? Or let me write it in the other sense. T is equal to MR. Now, I can do the following. I'll write this equation as T is M. Alpha is A over R. So it's going to be M over 2. R times alpha is A. T is equal to MA over 2. Now I can combine these two equations. M2G minus M over 2A is M2A. I think that all of that is M1, right? I called that to be M1. So be careful with your indices. M1, M1. So apparently M2G is M2 plus M1 over 2A. Or acceleration is M2 plus M1 over 2 over 2G. Tension in the rope we found above. Tension in the rope is M1A over 2. Tension in the rope apparently is M1 over 2 M2 M1 over 2 plus M2 times G. So we've found what we set out to find. Let's check units quickly. I've obviously reached my goal. How about the units? It's quite simple here. Masses cancel each other. G and A have the same units. How about for T? Two masses cancel here. Mg is T. Units also work fine. But let's also think. I have a very simple limit. What if M1 was 0? What would happen? If I have a very, very light pulley, then this should be free fall for the mass suspended from the pulley. So M1 goes to 0, A should go to G, and it does. If M1 is 0, M2 is cancelled, it's G. So limit, at least one limit is fine. So we probably found the correct result. Yes, question? Which one? This one? When we found A, I had two equations here. I already found T. I put it into the first equation, okay? Let's see. I'm taking this guy to the right. So M2 over M1 plus 2 times A. That's nothing wrong here. So it should be exactly the reverse. Thank you. See? M2 over M2 plus M1 over 2. That actually looks much better. T was M1 over 2 times A. So it's going to be M1, M2 over 2M2 plus M1 times G. So apparently, even though we do our checks, we can get something wrong. But it's always good to do our checks, okay? Now, let me remind you, on Thursday at 8:40, I'll be here. And we have some ground to cover about rotational motion. And the second hour will be a review for the exam, okay? Good.